Hello and welcome. In this video, we'll provide an overview of sequential data and explain why it poses a problem for traditional neural networks. Whenever the points in a dataset are dependent on the other points, the data is said to be sequential. A common example of this is a time series, such as a stock price or sensor data, where each data point represents an observation at a certain point in time. There are other examples of sequential data, like sentences, gene sequences, and weather data. But traditional neural networks typically can't handle this type of data. So, let's see why we can't use feed-forward neural networks to analyze sequential data. Let's consider a sequential problem to see how well-suited a basic neural network might be. Suppose we have a sequence of data that contains temperature and humidity values for every day. Our goal is to build a neural network that imports the temperature and humidity values of a given day as input and output. For instance, to predict if the weather for that day is sunny or rainy. This is a straightforward task for traditional feed-forward neural networks. Using our dataset, we first feed a data point into the input layer. The data then flows to the hidden layer or layers where the weights and biases are applied. Then the output layer classifies the results from the hidden layer, which ultimately produces the output of sunny or cloudy. Of course, we can repeat this for the second day and get the result. However, it's important to note that the model does not remember the data that it just analyzed. All it does is accept input after input and produces individual classifications for every day. In fact, a traditional neural network assumes that the data is non-sequential and that each data point is independent of the others. As a result, the inputs are analyzed in isolation, which can cause problems if there are dependencies in the data. To see how this can be a limitation, let's go back to the weather example again. As you can imagine when examining weather, there is often a strong correlation of the weather on one day having some influence on the weather in subsequent days. That is, if it was sunny on one day in the middle of summer, it's not unreasonable to presume that it'll also be sunny on the following day. A traditional neural network model does not use this information, however, so we'd have to turn to a different type of model, like a recurrent neural networks model. A recurrent neural network has a mechanism that can handle a sequential dataset. By now, you should have a good understanding of the problem that the recurrent neural network model is trying to address. This concludes the video. Thanks for watching. Hello and welcome. In this video, we'll provide an overview of recurrent neural networks and explain their architecture. A recurrent neural network, or RNN for short, is a great tool for modeling sequential data. The RNN is able to remember the analysis that was done up to a given point by maintaining a state or a context, so to speak. You can think of the state as the memory of RNN, which captures information about what's been previously calculated. This state recurs back into the net with each new input, which is where the network gets its name. Let's take a closer look at how this works. Imagine that the RNN we're using has only one hidden layer. The first data point flows into the network as input data, denoted as X. As we mentioned before, the hidden units also receive the previous state or the context, denoted as H previous, along with the input. Then, in the hidden layer, two values will be calculated. First, the new or updated state, denoted as H new, is to be used for the next data point in the sequence. And second, the output of the network will be computed, which is denoted as Y. The new state is a function of the previous state and the input data as shown here. If this is the first data point, then some form of initial state is used, which will differ depending on the type of data being analyzed. But typically, it is initialized to all zeros. Please notice that Wx in this equation is the weight matrix between the input and the hidden unit, and Wh are the weights that are multiplied by the previously hidden state in the equation. The output of the hidden unit is simply calculated by multiplication of the new hidden state and the output weight matrix. So, after processing the first data point, in addition to the output, a new context is generated that represents the most recent point. Then, this context is fed back into the net with the next data point, and we repeat these steps until all the data is processed. Recurrent neural networks are extremely versatile and are used in a wide range of applications that deal with sequential data. One of these applications is speech recognition. As you can see, it is a type of a many-to-many network. That is, the goal is to consume a sequence of data and then produce another sequence. Another application of RNN is image captioning. Although it's not purely recurrent, you can create a model that's capable of understanding the elements in an image. Then, using the RNN, you can string the elements as words together to form a caption that describes the scene. Typically, RNN has outputs at each time step, but it depends on the problem that RNN is addressing. For example, in this type of RNN for captioning, there is one input as image, and the output is a sequence of words. So, it is sometimes called one-to-many. RNN can also be many-to-one. That is, it consumes a sequence of data and produces just one output. For example, to predict a stock market price, where we might only be interested in the price of a particular stock in tomorrow's market. Or for sentiment analysis, where we may only care about the final output, not the sentiment after each word. We've only covered a few applications, but variants of the recurrent models are continuing to solve increasingly complex problems, which are beyond the scope of this video. Despite all of its strengths, the recurrent neural network is not a perfect model. One issue is that the network needs to keep track of the states at any given time. There could be many units of data or many time steps, so this becomes computationally expensive. One compromise is to only store a portion of the recent states in a time window. Another issue is that recurrent neural networks are extremely sensitive to changes in their parameters. As a result, gradient descent optimizers may struggle to train the net. Also, the net may suffer from the vanishing gradient problem, where the gradient drops to nearly zero and training slows to a halt. Finally, it may also suffer from the exploding gradient, where the gradient grows exponentially off to infinity. In either case, the model's capacity to learn will be diminished. By now, you should have a good understanding of the main ideas behind the recurrent neural network model. Thanks for watching this video.